When you look up at the night sky, everything appears calm enough to last forever. The moon arrives on schedule. The planets rise and fade in their ancient paths. The sun returns each morning with such unwavering certainty that it becomes easy to believe the oldest illusion in astronomy, that what we are seeing is permanence, a stable system, a finished design, a celestial arrangement that has already settled into its final form and will continue unchanged in any meaningful way for ages beyond imagination. It is one of the most comforting ideas the human mind has ever invented. And it is wrong. Our solar system is not stable. It is not permanent. It is not a completed machine turning peacefully in the dark. It is a system in motion at every scale, a place where nothing has truly stopped changing since the first dust began circling the newborn sun 4.6 billion years ago. Every orbit is still being negotiated. Every world is still being altered. Every moon is still being pulled, squeezed, heated, slowed, or pushed away. The sun itself, the great anchor at the center of it all, is consuming its own future second by second, following a schedule written by physics long before Earth had oceans, long before life took its first uncertain shape, long before any living thing could look upward and mistake change for stillness. The strangest part is that most of this destruction is invisible to us, not because it is hidden, but because it is slow. Human beings are creatures of short time scales. We notice fire when it flares, ice when it cracks, storms when they break the horizon. But the solar system unfolds according to a different rhythm, one measured not in breaths or seasons, but in millions of years, in billions of years, in rates so small that no human eye could ever naturally feel them. A moon moves away by a few centimeters. A planet loses a fraction of atmosphere to the solar wind. A star sheds mass at a rate so monstrous it should be impossible to imagine. Yet from our distance it still looks serene, golden, eternal. The machine does not shatter all at once. It erodes with discipline. And because that erosion is slow, it becomes easy to call it order. Tonight, as you lie beneath a sky that feels motionless, the moon is already farther away than it was yesterday. Not by much. About 3.8 centimeters each year, less than the length of a finger, a change so slight that it seems unworthy of fear. But that same tiny increase has been accumulating for immense spans of time, and it will continue. The moon is not simply orbiting Earth. It is leaving Earth. It is carrying angular momentum away from our planet, slowly lengthening our days, slowly changing the tidal relationship that once made Earth very different from the world we know now. This is not a theory waiting to be confirmed. Laser measurements have already told us it is happening. At the same time, the sun is losing mass every second. Not metaphorically, literally. Deep in its core, nuclear fusion turns hydrogen into helium, and in the process, a portion of that mass is converted into energy and radiated away into space. The number is difficult to sit with. Around 4 million tons of mass vanish every second into pure energy, every second, for billions of years. The star that makes all life here possible is not a fixed object preserving itself in perfect balance. It is a furnace consuming its own reserves on a timetable that cannot be negotiated, delayed, or reversed. One day that timetable will end in a transformed sun and a dead Earth. But long before that final transformation, the process is already underway. The ending is not waiting to begin. It began with the birth of the star. And elsewhere in the system, smaller tragedies are already in motion. Phobos, the larger of Mars' 2 small moons, is not drifting safely in place. It is spiraling inward, about 2 meters every century, slow enough to seem harmless, fast enough, over geological time, to become fate. In roughly 50 million years, it may cross the limit where Mars' tidal forces tear it apart, shredding the moon into debris that could briefly form a ring around the planet, a moon becoming a wound of stone around a dying red world. Far out at Neptune, Triton is following its own doomed path. Unlike Earth's moon, unlike many satellites that are slowly moving away. Triton is spiraling inward. It is trapped in a long inward fall that could one day destroy it completely, perhaps turning it into a ring system as well. The solar system is filled with these quiet one-way journeys. Some moons escape, some collapse inward, some are stretched, heated, and broken by gravity itself. And all of it is happening now. This is the truth hidden behind the calm appearance of the sky. The solar system is not a still life. It is an active process. There are at least 5 great forces running through it at all times, each one reshaping worlds in silence. Tidal forces are pulling on moons and planets, stealing energy from rotation, distorting interiors, shifting orbital distances, and heating frozen bodies from within. Solar wind is streaming outward from the sun, stripping atmospheres from worlds that cannot defend themselves, and slowly writing its influence across billions of miles of space. Gravitational interactions between planets continue to nudge, perturb, and sometimes destabilize orbits over immense timescales. Nuclear fusion in the sun steadily consumes the central engine of the entire system. And beneath all of it lies entropy, the deep rule that every structure, no matter how grand, must eventually decay, disperse, or transform into something simpler. If you place these processes side by side, the old illusion of permanence becomes difficult to maintain. Take the moon again. To us it seems ancient and unchanging, but the early Earth did not know the moon as we do. Long ago it hung much closer in the sky, enormous and oppressive, raising tides so violent they would have transformed coastlines into temporary landscapes of flood and retreat. Days were shorter then, Earth spun faster. The moon was not just a companion in the sky, it was a more immediate force, and as it continues to move outward, it is not merely becoming more distant, it is changing what Earth is allowed to be. Or consider Mars. Today it looks frozen, almost fossilized, a planet where time feels trapped in dust. But one of its moons is doomed to destruction, and the planet itself bears signs of having once been far more dynamic than the dry ruin we see now. Solar wind helped strip away much of its atmosphere after Mars lost the strong global magnetic field that may once have shielded it. What seems dead now was not always dead. What seems fixed now is often only what remains after change has already passed through. Venus offers a different version of the same warning. From a distance, it looks almost Earth, like in size, almost familiar in form. Yet its surface is a furnace, its atmosphere a crushing envelope of carbon dioxide and sulfuric clouds. Somewhere in its history, the conditions diverged so completely that one world became habitable and the other became a sealed catastrophe. Stability was never guaranteed. A planet can look complete and still be the aftermath of irreversible change. Jupiter appears eternal in another way, not delicate like the inner rocky worlds, but vast and overwhelming, almost too large to imagine as vulnerable. But Jupiter is not static either. Its gravity continuously rearranges the fates of smaller bodies, captures and redirects objects, stirs resonance chains among moons, and helps shape the architecture of the solar system in ways that can preserve or destroy. Even a giant planet is not simply sitting there. It is participating in an ongoing dynamical argument with everything around it. And then there is Saturn, whose rings look too exquisite to be temporary, too perfect to belong to time at all. Yet even they may be young on cosmic timescales, and they are slowly changing, raining material inward, evolving under the same merciless logic as everything else. Beauty is not proof of permanence. In the solar system, beauty is often what temporary balance looks like. This is the deeper discomfort in all of it. The things we call stable are often only slow. The sky does not reassure us because it is unchanging. It reassures us because its changes are too gradual for the nervous system we inherited. Human life is so brief that the solar system can perform catastrophic transformations while still appearing calm across the span of generations. A mountain seems permanent until geology is given enough time. A star seems eternal until stellar evolution is allowed to finish its sentence. A moon seems faithful until orbital mechanics reveal that it has been leaving all along. And once you understand that, the night sky becomes harder to look at in the old, innocent way. Because every familiar object becomes two things at once. The moon is both the white lantern above Earth and a body receding into the dark, carrying away part of our planet's rotational energy. The sun is both warmth and illumination and a giant fusion engine spinning itself toward an unavoidable end. Mars is both a silent red planet and a world whose moon is on a death spiral. Neptune is both a remote blue giant and the keeper of Triton's slow destruction. Even the emptiness between worlds is not inert. It is filled with solar wind, radiation, dust, gravity, magnetic structure, and the long invisible consequences of motion. Nothing is resting. Everything is becoming. There is a tendency in popular imagination to picture the solar system as a finished map. The planets are where they belong. Their moons accompany them. The sun burns at the center. Comets arrive and vanish. The basic arrangement is assumed to be settled. But that map hides the fact that every body in the system carries a timeline. Each one is moving through a history of change that extends both backward and forward, and those histories do not end in preservation. They end in transformation. That word matters more than destruction, because destruction sounds sudden, while transformation is what the solar system truly specializes in. Moons become rings, atmospheres become ruins, oceans freeze, boil, or vanish. Planets migrate in early epochs and then appear calm, only after the violence has passed. Ice worlds hide internal seas because gravity needs them from the inside. Stars brighten gradually until habitable zones shift, and once, living surfaces are left behind. The whole system is less like a set of objects on display and more like a vast chain of experiments still unfolding. In that sense, the most dangerous assumption in science may not be that the universe is hostile. It may be that the universe is finished. Because finished things can be trusted. Finished things can be described with confidence. Finished things can be inherited without fear that they are drifting out of alignment under your feet. But the solar system is not finished. It is mid-process. It always has been. We just arrived during a calm, looking interval, on one world, under one star, at one moment when the timescales happen to be kind enough to let intelligence emerge and mistake temporary balance for cosmic intention. Perhaps that is why these measurements feel so eerie once you let them sink in. They are not predictions about some fantastical future. They are not cinematic disasters waiting just beyond the horizon. They are statements about what is already underway. The moon is already moving away. The sun is already losing mass. Phobos is already falling inward. Triton is already descending toward an eventual destruction. Atmospheres are already being stripped where protection fails. Entropy is already dissolving every structure that can be dissolved. The endpoint may be far away. But the process is current. It is measurable. It is confirmed. It is happening tonight. And there is something almost hypnotic in the contrast between that truth and the way the sky still looks. You could step outside and see tranquility. You could see beauty, order, familiar lights, hanging in darkness with an ancient composure. You would not see the numbers. You would not feel the centimeters of lunar recession. You would not sense the millions of tons of solar mass vanishing into radiation this very second. You would not hear the tidal stresses inside distant moons or the slow inward fall of doomed satellites around remote planets. The eye receives peace. Physics tells a different story. That story is what makes the solar system worth listening to in the first place. Not because it is stable, but because it is alive with change. Not because it preserves itself, but because it reveals, with extraordinary clarity, what happens when gravity, energy, time, and matter are left together for long enough. The sky above us is not a museum. It is an unfolding event, and in the quiet chapters ahead, each world will show us a different version of that event. A moon leaving its planet. A star eating itself. Frozen ocean worlds kept liquid by invisible stress. Giant planets that once may have nearly destroyed the inner system before life ever had a chance to begin. Every one of them is a case study in the same hidden truth. The solar system is not simply existing. It is transforming toward outcomes that have already been written into its physics. So tonight, Before you let the familiar comfort of the heavens settle over you again, hold one thought a little longer than usual. What looks eternal is often only slow, and what looks stable may already be falling apart. Subscribe to Nocturnal Space, turn on notifications, and stay with me, because what is happening in our solar system right now, measurable, confirmed, and far stranger than most people realize, is one of the most unsettling stories in modern science. Tonight, while the world turns in its sleep, the moon is already farther away than it was last night. Not by much. Not enough for any human eye to notice. Not enough to disturb the tides in a way that would make anyone step back from a shoreline and feel that something ancient had shifted. But the change is real. Quietly, patiently, with a precision so fine it feels almost cruel, the moon is retreating from Earth by about 3.8 centimeters every year, a distance smaller than the width of a hand. A movement so modest it sounds harmless. And yet it has been happening for an astonishing length of time, accumulating through the entire deep history of our planet, carrying with it consequences so large that they reach into the length of our days, the stability of our climate, and the future shape of the sky itself. This is one of the strangest truths in planetary science. The moon, which so often appears to human beings as a symbol of recurrence, loyalty, and return, is not staying with us in any permanent sense. It is moving away. It is loosening its bond with Earth. It is, in the long language of orbital mechanics, leaving. That statement sounds almost poetic at first, but it is not poetry. It is measurement. On the lunar surface, left behind by astronauts during the Apollo missions, are arrays of retroreflectors, exquisitely simple instruments designed to do one thing with unforgiving honesty. They reflect laser light back in the direction it came from. From observatories on Earth, scientists fire pulses of laser light toward those reflectors and measure the return time with extraordinary precision. The beam travels to the moon, touches those silent mirrors, and comes home again. By repeating this over and over across decades, we have learned something unsettlingly intimate about our nearest celestial companion. Its distance is increasing. Not maybe. Not perhaps. Not as a speculative model waiting for confirmation. It is increasing, directly measured down to astonishing levels of accuracy. And once you know that, the moon becomes harder to see in the old innocent way. Because the moon is no longer just a bright disk in the dark. It becomes an event in progress. It becomes a body caught inside an exchange of energy with Earth, a slow theft of rotation transformed into distance. The mechanism behind it is subtle enough to sound almost beautiful. Earth spins faster than the moon orbits. That difference matters. The tidal bulges raised by the moon in Earth's oceans are pulled slightly ahead of the Earth, moonline, because our planet is rotating. Those bulges carry mass, and that mass carries gravity. The bulges pull on the moon, giving it energy, lifting it into a slightly higher orbit. At the same time, Earth loses rotational energy. Our planet slows down. The moon drifts outward. Angular momentum is not destroyed. It is transferred. Earth is gradually spending its spin to push the moon away. So while the moon retreats, our days lengthen. Not dramatically. Not enough for morning to surprise us with some visible collapse of timekeeping. The change is around 1.4 milliseconds per century. That sounds trivial, almost comically small, and on the scale of a human life it is. But the solar system does not care about human convenience. Given enough time, tiny rates become destiny. Hundreds of millions of years ago, Earth spun noticeably faster than it does now. Billions of years ago, days were shorter still. If you could stand on the early Earth, assuming anything like standing were possible amid its violence, you would not know the rhythm we call normal. You would know a world spinning under a much closer moon, with tides more powerful, days shorter, and a planetary balance very different from the one that eventually allowed forests, oceans, and mines like ours to emerge. This is what makes the recession of the moon so eerie. It is not only changing the future, it has already shaped the past. Around 1 billion years ago, Earth's day may have lasted only about 18 hours. Earlier still, after the Moon first formed in the aftermath of a catastrophic collision, it orbited much closer than it does now, perhaps only around 24,000 kilometers away. In the sky, it would have looked immense. Not the calm silver companion we know, but something dominating, almost oppressive. Tidal forces on Earth were far stronger then. The oceans responded to a nearer and more violent relationship. The coastlines, if coastlines existed in any recognizable sense, were part of a planet under a much more dramatic gravitational influence. Earth and Moon were not yet the elegant pair we imagine today. They were still settling into a long negotiation. And that negotiation is still not over. Perhaps the most haunting consequence of all is that the Moon is not merely decorative to Earth. It is not simply a lantern in the night or the author of tides. It is one of the hidden stabilizers of the entire planet. The gravitational pull of the Moon helps steady Earth's axial tilt, that crucial lean of about 23.5 degrees that shapes the seasons and the broad rhythm of climate. Without the Moon's influence, Earth would not necessarily remain so well behaved. Over immense timescales, the tilt of a planet can wobble, sometimes drastically, and those changes can alter climate in profound ways. The Moon acts in effect like a stabilizing weight on a spinning world. It does not freeze Earth into perfect constancy, but it restrains chaos. This is one of the least intuitive and most important facts about our existence. The Moon is not just orbiting Earth. It is helping preserve the conditions under which complex life has been possible. Mars offers a warning of what a less stabilized world can become. Unlike Earth, Mars has no large moon to serve as a comparable gyroscopic influence. As a result, its axial tilt has likely varied far more dramatically over geological time. In some periods, it may have leaned enough to transform its climate in extreme ways, redistributing ice, changing atmospheric behavior, perhaps even helping turn an already vulnerable world into a much harsher one. Mars reminds us that a planet's tilt is not a trivial detail. It can help decide whether climates remain relatively moderate or swing into catastrophic instability. Now imagine Earth without a moon strong enough to keep its long, slow balance. The change would not come quickly enough to frighten any single civilization in one dramatic motion. That is not how celestial mechanics usually works. It would unfold in patient instability. The tilt could drift more wildly over millions of years. Seasons could become more extreme. Climate zones could wander. The broad regularity that complex ecosystems have depended on might weaken. The Earth we call familiar would become less reliable. The important thing is not that this chaotic future has fully arrived. It is that the process that could one day allow it has already begun. Every centimeter the Moon moves outward slightly weakens its stabilizing grip. Again, the great terror of astronomy is not suddenness. It is continuity. The Moon continues to recede. Earth continues to slow. The equilibrium we inherited is not a permanent gift. It is a phase. There is another loss hidden in this recession, one small by geological standards yet strangely heartbreaking on the human scale. Total solar eclipses will not last forever. Right now, we live in a rare and beautiful era in which the Moon appears in the sky almost exactly the right size to cover the Sun's bright face during totality. It is one of the most astonishing visual accidents in nature. The Moon is about 400 times smaller than the Sun, but also about 400 times closer, allowing the two disks to match with haunting precision. That coincidence gives us eclipses of almost supernatural beauty, moments when the day collapses into blackness and the Sun's corona blooms around a perfect dark circle. But the Moon is moving away. And because it is moving away, that coincidence is temporary. In roughly 600 million years, the Moon will appear too small in the sky to fully cover the Sun. Total eclipses will end. Forever after, there may still be annular eclipses, rings of fire, imperfect coverings, but the complete extinguishing of the solar disk will no longer occur. One of the most sublime sights in the sky is not an eternal feature of the cosmos. It is a time-limited arrangement, and we happen to exist during the interval when it is still possible. That thought alone can change the atmosphere of an eclipse. It is no longer just beautiful. It is perishable. This is the pattern the moon keeps teaching if you listen carefully enough. Stability is often only a slow process of leaving. Beauty is often only a temporary geometry. We inherit conditions that feel natural only because the timescales involved are too immense for our instincts to interpret as motion. And Earth is not unique in this. Mars, as always, offers a more visibly wounded version of the same underlying physics. Its two small moons, Phobos and Deimos, are traveling in opposite orbital destinies. Deimos, the outer moon, is slowly moving away from Mars, much like our moon recedes from Earth. But Phobos, the closer moon, is doing the opposite. It orbits below Mars' synchronous radius, meaning it circles the planet faster than Mars rotates beneath it. The result is a reverse transfer of energy. Instead of being pushed outward, Phobos is being pulled inward. It is spiraling closer to Mars, descending in a long gravitational fall, about 2 meters every century. Again, the number sounds laughably modest. Again, over time, it becomes fatal. In around 50 million years, Phobos may cross the Roche limit, the distance at which tidal forces become strong enough to tear apart a body held together only by its own gravity and internal structure. If that happens, Phobos will not simply crash intact into Mars. It may be shredded into fragments, forming a temporary ring around the planet before those fragments eventually rain down to the surface. Imagine that. Mars, which now appears to us as a quiet red world attended by 2 insignificant moons, may one day wear a ring made from the remains of one of its own companions. 2 moons, one moving outward into greater distance, one moving inward toward destruction, both governed by the same quiet logic of tides and orbital mechanics. The difference between escape and death is not sentiment. It is position. There is something profoundly cold in that truth. Celestial bodies do not remain because they are beautiful together. They remain because the equations allow it. When the equations favor change, change arrives, whether slowly or violently. The same is true for Triton around Neptune, though on a much longer timescale. Triton is unusual, likely a captured object rather than a moon born neatly with its planet. Its orbit tells that story. It moves backward relative to Neptune's rotation, a retrograde path that marks it as an outsider. Because of that orbital relationship, tidal interactions are gradually drawing Triton inward. Far in the future, perhaps in 3.6 billion years, it could be torn apart as well, becoming yet another ring system born from the destruction of a moon. Even in the farthest reaches of the solar system, the same sentence is being written again and again. Tides reshape everything they touch. This gives the whole system a strange emotional unity. The moon leaving Earth, Phobos falling toward Mars, Triton descending toward Neptune, Deimos drifting away. Different worlds, different distances, different outcomes, all governed by variations of the same invisible mechanism. Gravity is not simply holding the solar system together. It is quietly editing it. And because all of this happens on timescales so much longer than a human life, the result is a kind of cosmic deception. We call the moon reliable because it rose over every civilization we remember. We call the tides dependable because they answer the moon with ancient obedience. We call Earth's seasons natural because they have held long enough for agriculture, language, empire, and memory to form around them. But reliability is not permanence. Dependability is not eternal design. A pattern can last for hundreds of millions of years and still be temporary in the larger logic of the system. This is the deeper discomfort beneath the moon's slow retreat. It reveals how many of the things we rely on are not fixed properties of the universe, but current expressions of an evolving relationship. Even time itself, as we live it, is wrapped into that relationship. Day length is not a constant handed down from the beginning. It is the current state of a slowing spin. The shape of the tides is not merely an oceanic habit. It is the signature of an ongoing gravitational exchange. The elegance of eclipses is not a fundamental law. It is a fleeting alignment between recession and distance, a coincidence with an expiration date. And all of this has been happening in the background of life's story. Dinosaurs lived under a slightly different moon. Earlier oceans rose under a closer one. The first land animals inherited different tides from the ones we know now. Every era of Earth has been lived beneath a sky participating in a gradual transformation too slow for biology to notice directly, yet powerful enough to shape the world that biology must adapt to. It is difficult not to feel something almost personal in that. The moon has always seemed emotionally available to the human mind. We write poems about it. We measure months by it. We send prayers and loneliness toward it. We imagine it as faithful because it returns. But astronomy has a way of stripping even the most beloved things down to process. The moon is faithful only in the short language of human generations. In the longer language of the solar system, it is already on its way out. And yet that does not make it less beautiful. It makes it more so. Because now every glance at the moon contains another layer of truth. You are looking at something ancient, but not fixed. Something stabilizing, but not forever. Something whose very presence helped shape the planet that shaped you, and which is already, with unimaginable patience, withdrawing from that role. The night sky becomes deeper when you understand that it is not preserving a perfect arrangement. It is displaying a moving one. Perhaps that is why the moon feels like the most intimate gateway into the larger truth about the solar system. It is close enough to be familiar, visible enough to be personal, and strange enough, once understood, to dissolve the old illusion that our celestial neighborhood is a finished machine. If even the moon is leaving, then nothing in the sky is standing still in the way our instincts want to believe. And what happens here, in the Earth, moon system, is only the beginning. Because if a moon can slowly alter the rotation of a planet, steady its axis, shape its tides, and then drift outward toward a future where those stabilizing effects weaken, then the solar system is not a set of isolated objects at all. It is a web of exchanges. Every orbit is a transaction. Every tidal bulge is a quiet redistribution of fate. Every world is changing not only because of what it is, but because of what it is touching gravitationally, endlessly, invisibly through time. The sky looks calm because the transactions are slow. But slow is not the same as safe. The moon is already leaving, and in its leaving, it is taking pieces of Earth's present with it. The shape of our days, the steadiness of our tilt, the future of eclipses, the long familiar partnership between planet and satellite that has helped make this world what it is. One day, that partnership will be weaker than it is tonight. One day, much later still, it will be unrecognizable. And that is what makes the moon so unsettling once you really know it. Not that it is distant, but that it is changing. Not that it is cold, but that it is involved in the fate of Earth far more deeply than most people ever imagine. Not that it lights the night, but that its very retreat is measurable, confirmed, and already underway. So the next time you see it rising, pale and composed above the horizon, try to hold both truths at once: the beauty and the mechanism, the calm and the departure, the ancient companion and the object already moving away by an amount too small to feel, yet large enough, over time, to remake the conditions of a world. And if that changes the way the moon looks to you tonight, subscribe and stay with me. Because the next great truth is even darker. While the moon is slowly leaving Earth, the sun itself is quietly consuming the future of everything that still remains. Every second, the sun destroys part of itself. Not in the violent, cinematic way the human mind prefers to imagine destruction. Not with cracks, screams, collapse, or visible signs of panic. The sun does not look like something dying. It looks serene, complete, golden. It rises with such confidence that entire civilizations built their calendars, prayers, harvests, and certainties around its return. No object in the sky feels more permanent. No light feels more trustworthy. The sun appears less like an event and more like a law. And yet beneath that appearance is one of the strangest and most merciless processes in the universe. At its core, the sun is not resting. It is burning through itself with perfect discipline. Every second, roughly 600 million tons of hydrogen are fused into helium. But the arithmetic of stars is not clean in the way the eye would expect. Of those 600 million tons, only about 596 million emerge as helium. The missing 4 million tons are not lost in the ordinary sense. They are converted into pure energy, radiated outward as the sunlight and heat that fill the solar system. 4 million tons of mass vanish every second into light. Every second. Not once in a great flare of cosmic violence, but continuously, without hesitation, without pause, through all the ages of Earth. It is difficult to sit with that number long enough for it to mean anything. 4 million tons each second sounds like the exaggeration of myth. Yet this is the quiet accounting at the center of our star. The sun shines because it is spending itself. The warmth on your skin, the brightness of morning, the stability of seasons, the energy that feeds oceans, forests, winds, and every green leaf on Earth, all of it comes from a process of loss. The sun is not giving us surplus. It is giving us its future. This is the first correction that changes everything. The sun is not eternal. It is an engine with reserves, and those reserves are being consumed right now. For about 4.6 billion years, this process has continued in the core. Hydrogen nuclei, under crushing pressure and impossible temperatures, overcome their mutual repulsion and fuse into helium. The details are buried in nuclear physics so extreme that it almost ceases to feel physical at all. Temperatures of around 15 million degrees Celsius, pressures beyond ordinary intuition, matter packed into a regime where the rules of daily life are simply no longer relevant, and at the heart of all that, a slow miracle of conversion. A star making light by turning mass into energy. It sounds stable because it is regular, but regular is not the same as permanent. The sun can only continue this for as long as it has hydrogen in the right places under the right conditions. And although its timeline is mercifully vast compared with human history, it is not infinite. The star is moving through a life cycle written into its mass from the day it formed. Its brightness, its temperature, its future expansion, even the eventual destruction of the inner planets are all downstream from that one fact. The sun is not merely shining, it is aging. And it has been aging the entire time life was learning how to exist beneath it. This matters more than most people realize, because the sun is not constant even now. It only appears constant when measured against the shortness of human life. Across the billions of years since its birth, the sun has gradually become brighter. Not dramatically from one century to the next. Not enough for ancient observers to realize that the star overhead was changing. But enough, over geological time, to rewrite the conditions of entire worlds. When the Earth was young, the sun was dimmer than it is today, perhaps around 30% less luminous. That should have made early Earth a frozen world, too cold for liquid oceans. And yet, the geological record tells a different story. There was liquid water. There was chemistry. There was the long, early groundwork of habitability. This is one of the great quiet puzzles of planetary science, the faint young sun paradox. Somehow, Earth stayed warm enough under a weaker star, likely because its atmosphere was richer in greenhouse gases, trapping more heat than our present air does. The important point is not only that Earth solved that paradox, it is that the sun itself was different then. The star that warmed the first oceans was not the same star that shines on Earth now. And the sun of the future will be different again. This is where the story begins to darken. As hydrogen fuses into helium in the core, the composition there changes. Helium is denser. It does not fuse under the sun's current central conditions in the same way hydrogen does, so the core gradually accumulates helium ash, and as it does, the inner structure of the sun shifts. The core contracts slightly under gravity. That contraction raises temperature and pressure. Fusion in the surrounding hydrogen becomes more efficient, and so, very slowly, the sun grows brighter. This means the sun's future is not only eventual death, it is increasing hostility long before death arrives. In about 1 billion years, the sun may be roughly 10% brighter than it is now. That sounds modest. It sounds survivable. But planetary climate does not always respond gently to modest changes in stellar input. Earth's surface is balanced on a delicate system of feedbacks involving oceans, atmosphere, ice, carbon cycles, cloud formation, and chemistry. A 10% increase in solar luminosity is enough to push that balance toward catastrophe. A runaway greenhouse effect could begin. Oceans would warm. More water vapor would enter the atmosphere. Water vapor itself is a greenhouse gas, amplifying the warming. More heat leads to more vapor, which leads to more trapped heat, which leads to still more vapor. The feedback tightens. At some point, Earth would no longer be the blue planet we know. The oceans would begin to evaporate in a sustained way, not as a dramatic boiling overnight, but as a long surrender. The atmosphere would thicken with water vapor. Ultraviolet light from the sun would split some of those water molecules in the upper atmosphere. Hydrogen, the lightest element, would escape into space. Ocean by ocean, molecule by molecule, the water that made life possible would be dismantled and lost. Even before the final red giant catastrophe, Earth would become a world in retreat from habitability. This is one of the most unsettling things in modern astronomy. Earth's ultimate end does not begin with engulfment. It begins with warmth. A billion years from now, the sun may still look to a distant observer like a perfectly normal star. There will be no visible sign of doom in its face. Yet, on Earth, or whatever remains of Earth's surface then, the conditions for complex life may already be collapsing. The biosphere would be pushed into shrinking refuges, if any remain at all. Oceans would retreat. Climate systems would fracture. What we call life, friendly, would become a memory of a cooler age. The star does not need to die to kill us. It only needs to continue being what it already is, a fusion engine getting steadily brighter as it ages. This gives the sun a strange dual identity. It is the author of life and its eventual executioner. Every forest, every coral reef, every animal migration, every cloud, shadow crossing a field, every heartbeat powered indirectly by sunlight, all of it exists because the sun burns. And because the sun burns, all of it is also temporary. The very source of Earth's habitability contains within it the timetable for Earth's ruin. There is no separate villain waiting in the dark. The danger is the same light that made everything possible. And then, much later, comes the transformation so dramatic that even the language of endings begins to feel too small. In roughly 5 billion years, the sun's core hydrogen will be exhausted. Not all hydrogen in the star, but the hydrogen in the central region where the current fusion process can be sustained. When that happens, the balance that has held for billions of years will fail. Fusion in the core will cease. Without that outward pressure, gravity will begin to compress the core further. Temperatures will rise. Hydrogen fusion will continue in a shell around the inert helium core, and the outer layers of the sun will respond in the only way stars of this kind can. They will expand. The sun will become a red giant. This is not a metaphor. It is not a poetic name for slight aging. The sun will swell enormously, changing from the yellow star we know into a vast red giant star with a diameter that may extend out toward the current orbit of Earth. Mercury will be gone. Venus will be gone. The inner solar system will be transformed into something almost unrecognizable. The familiar architecture of the sky, the ancient order of mornings and seasons and orbital companionship, will be dissolved into heat and expansion. Earth's exact fate in that final phase is still discussed in models. Some calculations suggest Earth may be engulfed outright by the sun's expanded outer layers. Others suggest it may spiral outward somewhat as the sun loses mass, perhaps narrowly avoiding total engulfment. But this uncertainty is almost cosmetic. In either case, the Earth we know will be finished long before. If the planet survives physically for a while, it will survive as a scorched ruin, its surface blasted, its oceans absent, its atmosphere altered beyond recognition, its crust perhaps partly molten, all signs of habitability erased. The distinction between being destroyed and surviving as an inferno is not a comforting one, and there is an even more chilling subtlety hidden inside this future. As the sun brightens and the habitable zone moves outward, there may be a brief era when worlds once thought too cold become more temperate. Mars could pass through a temporary period of relative habitability. The icy moons of the outer planets, places like Europa or Enceladus, could experience changes as sunlight reaches them in new ways. For a fleeting interval, the death of one habitable world may cast a softer light on others. The zone of life moves outward while the inner worlds burn. Even in destruction, the solar system rearranges opportunity with indifference. It is a beautiful thought until you remember what it costs. The sun, then, is not merely consuming itself at the center. It is rewriting the entire map of habitability as it ages. The regions where liquid water can exist shift. The chemistry of atmospheres changes. Entire planets pass from possible refuge to furnace, or from icebound silence to temporary thaw. Stellar evolution is not a local event. It is a system, wide command, issued slowly enough that no one alive could ever see the whole order unfold, yet decisively enough that every world obeys. And that command is already in progress. But even before the far future of red giants and dead oceans, the sun is affecting worlds more quietly through another mechanism, one less dramatic than fusion but still deeply destructive: the solar wind. Every second, the sun throws about 1 million tons of material into space in a continuous stream of charged particles. This wind is not merely an atmospheric leak. It is a persistent extension of solar force across the system. On Earth, we are partly protected by the magnetosphere, the magnetic field generated by motions inside our molten core. That field helps deflect much of the solar wind, shielding the atmosphere from being stripped away wholesale. It is not perfect protection, but it is enough to matter enormously. Mars was not so fortunate. Billions of years ago, Mars likely had a thicker atmosphere and stable liquid water on its surface. River valleys, delta structures, mineral evidence, all of it points toward a wetter and more active past. But Mars is smaller than Earth. Its core cooled more quickly. Its global magnetic field faded. Once that shield weakened, the solar wind could interact far more directly with the Martian atmosphere. Over immense spans of time, it helped strip much of that atmosphere away, leaving behind the cold, thin, fragile shell that exists today. Missions like MAVEN have measured that process in action, showing how solar particles continue to erode the atmosphere even now. Mars is not simply dry because it got unlucky once. Mars is still being changed by the sun. That should be unsettling, because it reveals how much a planet's survival depends not only on distance from the sun, but on its ability to defend itself against the star's continuous outflow. A magnetosphere is not just an exotic planetary feature, it is a long-term survival system. Earth still has one. But even Earth's magnetic field is not eternal in the way ordinary intuition wants permanence to be eternal. The geological record preserves evidence of magnetic reversals, times when the field weakens, reorganizes, and the magnetic poles switch places. These reversals have happened many times in Earth's history. The last major one was around 780,000 years ago. During such transitions, the field can weaken significantly before recovering. The exact consequences vary, and they are not likely to be extinction events by themselves. But they are reminders of the same broader truth that governs everything else in the solar system. Protection is not static. Shields fluctuate. Stability is often a managed condition, not a guaranteed one. This is what makes the sun so terrifying, once you stop thinking of it as scenery. It is not merely hanging there in the sky, warm and distant. It is spending mass, increasing brightness, throwing charged particles into space, rewriting climates, sculpting atmospheres, determining futures, and carrying the eventual destruction of the inner solar system inside its own normal life cycle. The star is not waiting to become dangerous. It is dangerous in the same act that makes it life, giving. And yet, to the human eye, none of this is visible. That is always the most hypnotic part of astronomy. The most consequential events often wear the calmest faces. You can stand in the morning sun and feel reassurance. You can close your eyes beneath its warmth and feel held by something ancient and benevolent. And in one sense, that feeling is earned. The sun has fed every living process on Earth. Without it, there would be no weather, no green world, no biological time. But in another sense, the reassurance is an illusion created by the mismatch between stellar timescales and human ones. We confuse continuity with kindness. We confuse repeated return with permanence. The sun returns because the schedule has not finished yet. That is all. The deeper truth is colder. The sun is a machine of temporary balance. It is living through a long middle age that allows a planet like ours to bloom, but the forces that will one day sterilize Earth are not separate from the forces warming your skin right now. They are the same physics, stretched across time. The light that nourishes the biosphere is the light generated by a star, exhausting its core hydrogen. The winds that paint auroras across polar skies are part of the same stellar outflow that can strip weaker worlds bare. The eventual red giant is not a new sun arriving from elsewhere. It is this sun, continuing honestly into its future. Perhaps that is why the sun deserves a different kind of awe than we usually give it. Not the simple awe of brightness, but the slower awe of understanding. To look at the sun properly is to look at a system in the act of spending itself for billions of years with perfect consistency. It is to see not only the present warmth, but the future desert, not only the source of life, but the expiration date written into the mechanism, not only a star, but a timeline. And timelines are what the solar system is made of. The moon has one, Mars has one, Phobos has one, Triton has one, Saturn's rings have one, Earth's magnetic shield has one, and the sun's timeline is the one that frames all the others. It determines how long oceans can exist, how far habitable conditions extend when the inner worlds begin to fail, and what kind of strange temporary opportunities may open in the cold outer reaches as the star expands and changes. The system is not at rest. It is moving through these timelines right now, even as the sky looks calm enough to make us forget that anything is happening at all. But something is happening. The sun is losing 4 million tons of mass every second. The sun is becoming brighter. The sun is blowing material outward through the heliosphere. The sun is carrying Earth toward a future where oceans disappear and habitability ends. And one day, the sun will swell into a red giant and erase the familiar inner solar system almost completely. The ending is distant. The process is current. That is the quiet horror of it. So the next time the morning light spills across a wall, a field, or the edge of your bed, try to imagine what that light really is. Not just comfort, not just dawn, but matter converted into energy in the core of a star that is spending itself with flawless patience. Try to imagine that every sunrise is part of a countdown too long for human fear to properly hold, yet real enough to define the eventual fate of every ocean, every continent, every breathing thing that has ever depended on this star. And if that changes the way the sun feels to you tonight, stay with me, because the next truth is stranger still. Beyond the heat and the dying light, hidden in the frozen outer worlds, the solar system has been keeping oceans alive in darkness, and what those secret oceans may contain could change forever what we think life is allowed to become. Beneath the ice of Europa, there may be an ocean larger than all the oceans of Earth combined. That sentence should feel impossible. Europa is a moon orbiting far from the sun, nearly 778 million kilometers away, in a region of the solar system where sunlight is weak, where surface temperatures are brutally cold, where any ordinary intuition about life or habitability should have frozen into silence long ago. And yet under that hard, fractured crust, beneath kilometers of ice that look from space like a broken shell of stone, white glass, there may be a dark ocean held in liquid form not by sunlight, not by atmospheric warmth, not by anything the human species once thought necessary for a living world, but by stress. That is one of the most unsettling discoveries in modern planetary science, because it suggests that life, or at least the conditions for life, may not depend on the sun nearly as much as we once believed. For a very long time, the map of habitability seemed simple enough. If you want liquid water, you stay close enough to a star. Not too close, where water boils away into steam and the planet becomes a furnace. Not too far, where water freezes and remains trapped in permanent ice. Somewhere in between is the habitable zone, the narrow ring around a star where liquid water can exist on a planet's surface. It is a clean idea, elegant, easy to teach, easy to imagine. And for Earth, like surface conditions, it remains useful. But the solar system has a habit of punishing every idea that feels too neat, because far beyond the traditional habitable zone, in the realm of Jupiter and Saturn, where sunlight is only a pale memory of what it is on Earth, entire worlds may still be hiding liquid water, not on the surface where we can see it, not under blue skies or drifting clouds, but buried in darkness beneath thick shells of ice, oceans without sunlight, seas without weather. Water kept warm not by day but by gravity itself. Europa is one of the clearest and most haunting examples. At first glance, it does not look alive. Nothing in the usual human sense of the word seems possible there. The surface is frozen, bright, and scarred with long reddish cracks that cross one another like the marks on something under unbearable strain. There are few large impact craters, which is strange in itself. It suggests the surface is young, continuously renewed in some way, reshaped often enough that the older wounds of bombardment have been erased. That alone tells a quiet story. Europa is not geologically dead. Something beneath the surface has been active. The answer, as far as we can tell, is tidal heating. This is one of the most beautiful mechanisms in the solar system because it is so invisible and so violent at the same time. Europa orbits Jupiter, a planet so massive that its gravity is almost difficult to emotionally comprehend. But Europa's orbit is not perfectly circular. It is slightly elliptical, and because of that, the strength of Jupiter's pull changes subtly as the moon moves closer and farther in its path. Europa is squeezed and released over and over again. Its shape flexes. Its interior bends under stress. That repeated distortion generates heat through friction. In other words, Europa is being worked from within by gravity, kneaded in the dark, warmed by its own forced deformation. Jupiter is not merely holding Europa in orbit. Jupiter is crushing heat into it. That heat may be enough to maintain a global ocean beneath the ice shell. Pause long enough to feel what that means. There could be a world of liquid water hidden in darkness below a frozen surface, warmed not by any sunlit climate, but by the mechanical pressure of a giant planet pulling on it in endless cycles. Waves may move there. Currents may circulate. Minerals may dissolve from rock below. Chemistry may persist for billions of years completely isolated from open sky. If there are hydrothermal vents at the seafloor, as many scientists suspect might be possible, then Europa may contain something even more profound than an ocean. It may contain one of the most promising environments for life in the solar system. That possibility becomes even more unsettling when placed beside life on Earth, because here, in the deep oceans of our own planet, we have already discovered ecosystems that do not depend on sunlight at all. Around hydrothermal vents on the seafloor, life thrives using chemical energy rather than photosynthesis. Entire communities of organisms exist in darkness, drawing energy from reactions between water and minerals rising from Earth's interior. These places changed biology forever because they proved that sunlight is not the only engine life can use. Once that became clear, the outer solar system began to look different. Europa was no longer just an icy moon. It became a question. If darkness and water and chemistry are enough here, then what is sleeping there? That question grows even stranger when you look at Io, Europa's volcanic neighbor, the innermost of the large Galilean moons. Io is perhaps the most violently geologically active body in the solar system. Its surface erupts with volcanoes so powerful that plumes of sulfur and gas can rise hundreds of kilometers into space. The entire moon is a wound of lava and sulfur, resurfaced so constantly that impact craters barely survive. It is being squeezed even harder than Europa, tormented by Jupiter's gravity and by orbital resonances with the other moons that prevent its orbit from settling into something calmer. Io shows tidal heating at its most brutal. Europa shows a quieter version of the same process. On one moon, gravity produces hell. On another, it may produce a hidden ocean. The solar system keeps repeating the same lesson in different forms. The forces that destroy can also preserve. The same mechanism that melts rock on Io may keep water liquid on Europa. And Jupiter is not the only world doing this. Far out at Saturn, Enceladus tells an equally astonishing story, perhaps even more intimate because we have already tasted part of what lies below its surface. Enceladus is a small, icy moon, tiny compared with Earth, cold enough from the outside to seem hopeless. But at its south pole, great fractures open in the ice, and from them, plumes of water vapor, ice grains, salts, and organic compounds are blasted into space. Cassini flew through those plumes. It sampled material from the hidden ocean beneath without having to drill through kilometers of ice. What it found changed everything. Water, organic molecules, salts, molecular hydrogen. That last discovery matters tremendously. Molecular hydrogen in that context suggests water, rock interactions at the seafloor, possibly hydrothermal activity. On Earth, hydrothermal vents produce the kind of chemical gradients that life can exploit. The implication was chilling in the best way. Enceladus does not merely have a subsurface ocean. It may have the kind of chemical energy source that can support biology. And Enceladus is even farther from the sun than Europa. By the old textbook definition, these should be dead places, frozen storage worlds, geological leftovers, too cold, too distant, too abandoned by sunlight to matter. And yet they may hold some of the most habitable environments in the entire solar system, not on the surface where ancient human intuition would have searched, but beneath it, hidden, pressurized, dark, alive perhaps not with organisms, but at least with possibility. This forces a deeper correction to the map of life. The traditional habitable zone assumes that the star is the central story. But Europa and Enceladus suggest another possibility, that planetary systems may create local pockets of habitability through tidal heating alone. A gas giant can act almost like a second kind of energy source, not through light, but through gravitational stress. This means that moons orbiting giant planets could host liquid water environments even far outside the classic habitable zone. In some systems, there may be more potentially habitable moons than planets. In some cases, the true inventory of life, friendly places in the galaxy, may be vastly larger than we once estimated. The implications are almost too large to hold in one thought. Because if that is true, then the universe may not require a planet like Earth nearly as often as we assumed. It may only require water, chemistry, and an energy source that can persist. A moon orbiting a giant world in the dark may be enough. The number of places where life could emerge would then expand beyond the narrow ring around a star and spill outward into a broader, stranger landscape. The galaxy would become less a collection of isolated habitable planets and more a place where habitability can hide in ice, in pressure, in tidal distortion, in shadows. And then there is Ganymede, Callisto, Titan. The more closely we look, the less exceptional Europa and Enceladus seem. Ganymede, the largest moon in the solar system, may also contain a deep subsurface ocean, perhaps layered between ice and rock. Callisto may have one as well. These are not small hints anymore. They are a pattern. The outer solar system is not simply a cold graveyard of frozen spheres. It is a region where liquid water may be stored in enormous quantities beneath the visible skin of worlds that from the outside appear silent. But Titan deserves its own kind of dread, because Titan suggests that even water might not be the only path. Saturn's great moon. Titan is wrapped in a dense atmosphere, thick with nitrogen and rich in organic chemistry. On its surface, rivers flow, lakes collect, rain falls, but not rain made of water. Titan is so cold that water is hard as rock. The active fluid there is methane and ethane. Its rivers, lakes, and seas are hydrocarbons. It has weather, shorelines, and cycles of evaporation and condensation, but in a chemistry utterly alien to the one that shaped life on Earth. Beneath its icy crust, Titan may also contain a subsurface ocean of liquid water mixed with ammonia. So in one moon, you have both a deep hidden ocean and a surface world where exotic carbon chemistry plays out under an orange sky. That makes Titan more than strange. It makes Titan destabilizing to our assumptions, because Titan asks a quieter but perhaps more radical question than Europa does. Europa asks whether life can exist in dark oceans beneath ice. Titan asks whether prebiotic chemistry, or perhaps even some form of life, can operate in environments that do not rely on liquid water at the surface at all. The chemical pathways would be slower, colder, more alien, but not necessarily meaningless. If Earth taught us that life can emerge from chemistry under the right conditions, Titan asks how wide the phrase right conditions might actually be. This is why missions like Europa Clipper, JUICE, and Dragonfly matter so much. Europa Clipper will not land on Europa. It does not need to. It will fly by repeatedly, studying the ice shell, the chemistry of the surface, the thickness of the crust, the possible exchange between the hidden ocean and the frozen exterior. If plumes are present, material from the ocean may be sampled indirectly. JUICE will study the icy moons of Jupiter more broadly, with particular attention to Ganymede. Dragonfly, on Titan, will move from place to place in that dense atmosphere like a mechanical insect or dream, analyzing organic chemistry in a world where the familiar categories of biology and geology begin to blur. And what these missions find may change the emotional structure of science itself. If Europa or Enceladus shows signs of biology, not mere organic chemistry, not only water but actual biosignatures, then one of the most extraordinary barriers in human thought will collapse. Life would no longer be a phenomenon known from only one world. It would become a process the solar system can produce more than once. And if life emerges in two fundamentally different settings within the same system, then the universe may not be reluctantly alive. It may be inclined toward life whenever conditions allow. On the other hand, if these oceans are rich in chemistry and energy and still prove lifeless, that too will matter. It would tell us that the jump from chemistry to biology may be rarer or more delicate than we hope. Even absence would sharpen the question. That is what makes these ocean worlds so powerful. They are not just places. They are tests. Tests of whether life requires sunlight. Tests of whether water alone is enough. Tests of whether biology is rare, inevitable, or something in between. Tests of whether the old Earth-centered map of habitability was only a local accident mistaken for a law. And beneath all of this lies the deeper terror of the outer solar system, that so much can be happening where almost no sunlight reaches. Human intuition wants life to bloom under warmth, under blue sky, under visible energy. But the solar system keeps building possible refuges in darkness. Under the ice of Europa, under the fractured crust of Enceladus, perhaps under layers of Ganymede and Callisto, chemistry may have been operating for immense ages without ever seeing a sunrise. These are worlds where gravity replaces daylight, where internal heat replaces weather, where oceans are hidden from the cosmos by miles of frozen armor. There is something almost monastic about that image. Whole seas in darkness, pressure instead of sky, chemical gradients instead of seasons, silence above, motion below. And yet silence is not death. That may be the central revelation of these worlds. The absence of sunlight does not equal the absence of energy. The absence of atmosphere does not equal the absence of water. The absence of visible activity does not equal the absence of habitability. The solar system is teaching us, with almost embarrassing persistence, that life-friendly environments may exist in places we once would have dismissed as unworthy of a second glance. What makes this even more unsettling is how completely hidden these worlds are from casual perception. If you looked at Europa without knowing its story, you would see ice. If you looked at Enceladus from afar, you might see a small, bright moon and assume nothing more. Titan would seem alien, yes, but perhaps sterile. And yet, under those surfaces or within those atmospheres, processes may be unfolding that challenge the very architecture of how we classify living possibility. The old map of the solar system was built from surfaces. The new one is being built from interiors, and interiors change everything. They remind us that a world can look dead and still contain oceans. A moon can be frozen outside and active within. A body can sit far beyond the traditional warmth of a star and still host the chemistry of habitability. Once you understand that, the solar system becomes denser with possibility. Every icy crust becomes suspicious. Every plume becomes a message. Every gravitational resonance becomes a hidden heat source. The darkness of the outer worlds stops looking empty and starts looking secretive. That is perhaps the most powerful thing these moons are telling us. Not that they are alive, not yet, but that the universe may be under no obligation to make life obvious. It may hide it under ice. It may feed it through chemistry instead of light. It may allow it to emerge in oceans no human eye will ever directly see. It may build it on timelines so deep and in environments so strange that our first reaction is not recognition, but disbelief. And if that is true in our own solar system, then every star in the galaxy becomes harder to think about casually. Every giant planet may host moons with secret oceans. Every dark orbit may hold unseen chemistry. The census of habitable places expands not by a little, but by orders of magnitude. The universe becomes more crowded with maybe. That word maybe is what makes these worlds so hypnotic. Europa may host an ocean capable of supporting life. Enceladus may contain hydrothermal chemistry in darkness. Titan may be rehearsing an alternate version of prebiotic history. Ganymede and Callisto may be quieter members of the same hidden family. None of this is fantasy. None of it requires magic. It is all physics, pressure, chemistry, time. The same forces that are gradually dismantling the solar system in one place are preserving liquid oceans in another. That inversion matters. It means the solar system is not simply a collection of threats and endings. It is also a machine for creating unexpected refuges. Tidal stress may rip moons apart eventually, but before it does, it can warm them, crack them, liquefy them, and perhaps give chemistry enough time to become something more. The line between destruction and habitability is thinner than we were ever taught to imagine. So when you picture the outer solar system now, do not picture only frozen silence. Picture oceans in darkness. Picture moons under stress, not dead but enduring. Picture hidden water moving under ice while the sun hangs far away, dim and almost irrelevant. Picture the possibility that life may not need a blue sky at all, only energy, chemistry, and time. And then let that possibility widen until it reaches every giant planet around every other star. Because if worlds like these can be alive in principle, then the galaxy may be filled with hidden seas. And if that thought stays with you tonight, stay with me, because the next truth is even more destabilizing. The solar system we live in did not quietly settle into its present form. It almost destroyed itself before Earth ever had a chance to exist. 4 billion years ago, the solar system may have come very close to becoming a place where Earth never formed at all. That is one of the most unsettling ideas in planetary science, because it attacks a comfort so deep we rarely notice we are carrying it. When most people imagine the solar system, they imagine inevitability. The planets seem arranged as though they belong where they are. Mercury close in, then Venus, then Earth, then Mars, followed by the giants farther out, all of it feeling less like an accident than a finished architecture. Even when we learn that planets formed from dust and gas around a young star, we still tend to imagine the final result as something natural, almost destined. Of course, Earth ended up here. Of course, Jupiter formed far away. Of course, the inner planets remained rocky while the giant worlds ruled the cold outer dark. The map feels too orderly to have almost failed, but it may have almost failed completely. There is a modern idea in planetary science, now taken seriously because it explains several otherwise awkward features of our system, that tells a much stranger story. It suggests that Jupiter, the massive giant we often imagine as a distant guardian of the inner planets, may once have moved inward toward the sun so dramatically that it nearly erased the very material from which Earth and its neighbors would later emerge. In other words, the world we live on may exist only because Jupiter changed its mind. The name for this idea is the grand tack. The phrase sounds almost playful, like something a sailor would say, and that is not an accident. A tack is the turn a sailboat makes when changing direction against the wind. Jupiter, according to this picture, did something like that in the early solar system. It formed farther out in the protoplanetary disk, in a region rich enough in gas and solid material to build a giant planet quickly. But once formed, it did not remain quietly where it began. The young solar system was still full of gas then, a thick circumstellar disk surrounding the newborn sun. Giant planets embedded in such disks do not simply sit still. They interact gravitationally with the gas around them. They exchange angular momentum. They can migrate. And migrate Jupiter did. The giant planet may have moved inward from its birthplace toward the sun, plowing through the disk like a gravitational blade. This was not a little drift, not a trivial shift of position that only mathematicians would care about. In many versions of the model, Jupiter may have moved inward as far as around 1.5 astronomical units, roughly near where Mars now resides, deep enough into the young inner solar system to disrupt the material from which rocky planets were trying to assemble. If that inward migration had continued too long, Earth might never have existed. That is the sentence worth holding still in the dark for a moment. The giant world we now imagine as a distant outer monarch may once have been the destroyer of the inner system. It may have swept away or scattered much of the material that otherwise would have gone into building larger rocky planets. It may have truncated the region where Mars was forming, robbed the inner disk of mass, and rewritten the architecture of the entire solar system before the terrestrial planets were fully born. This does not just make the past more violent. It makes the present less inevitable. One of the long-standing puzzles in our system is Mars itself. Mars is small, much smaller than simple early formation models would have predicted for a planet forming where it sits. Why should the solar system have built Earth and Venus as substantial rocky worlds, only to leave Mars underweight, almost stunted, as though something interrupted the process? The grand tack offers an answer. Jupiter's inward migration may have swept material out of the region where Mars was growing, leaving it starved and incomplete. Mars, in this view, is not simply a naturally small planet. It is the surviving witness of an early catastrophe. The asteroid belt tells a similar story. It sits between Mars and Jupiter like a graveyard of failed planet formation, a region full of debris where a planet might have formed, but never did. Classical models struggled to explain why so little mass ended up there compared with what might have been expected. Again, Jupiter offers a brutal solution. Its migration would have stirred, scattered, and depleted that region, making it difficult for a planet to ever finish assembling. What remains now is not the residue of peaceful incompletion. It may be the wreckage left behind by the passage of a giant. And yet Jupiter did not keep going. This is where Saturn enters the story, and where the whole system may have been rescued by timing so precise it almost feels fictional. As Jupiter moved inward, Saturn was forming farther out. Like Jupiter, Saturn also interacted with the gas disk and began migrating. Eventually, the two giant planets may have become locked in an orbital resonance, their periods settling into a ratio that linked their motions gravitationally. Once caught together in this resonant dance, the balance of forces between them and the gas disk changed. Instead of Jupiter continuing to fall inward alone, the pair began moving outward together. Jupiter turned. That turn, the tack itself, may be one of the most important directional changes in the history of our system. Had it not occurred, Jupiter might have continued inward long enough to clear out the inner disk so completely that no Earth-like planet would remain. There would be no blue world, no oceans, no moon, no forests, no languages, no species capable of reconstructing the event billions of years later. The inner solar system as we know it may depend on the moment when Saturn caught up enough to pull Jupiter back outward. There is something deeply unnerving in that. Earth may not exist because the solar system was inherently favorable to life. Earth may exist because two giant planets happened to enter a resonance at the right time inside a young gas disk before the whole inner architecture was destroyed. This is the kind of fact that changes the emotional structure of astronomy. It means the solar system was not quietly prepared for us. It was nearly ruined before we ever had a chance. And even after that rescue, peace did not follow immediately. The early solar system remained a place of migration, collision, scattering, and delayed violence. Dust became rocks. Rocks became planetesimals. Planetary embryos collided, merged, and sometimes broke apart. Water and organics may have been delivered inward from colder regions. The architecture we see now emerged not as a polished design, but as the surviving pattern after repeated rounds of disruption. Stability, once again, was not the default. It was the temporary shape left behind by conflict. Perhaps nowhere is that more obvious than in another powerful framework for the solar system's early evolution, the Nice model. Named after the city in France where it was developed, the Nice model describes a later phase of dynamical instability among the giant planets, long after the gas disk had dissipated and the system might have seemed to any distant observer already largely assembled. Jupiter, Saturn, Uranus, and Neptune did not simply remain frozen into their final modern configuration from the beginning. According to this picture, they experienced a delayed instability triggered by orbital resonances, particularly involving Jupiter and Saturn. Once certain resonances were crossed, the gravitational consequences rippled outward. Neptune may have been flung farther outward into a disk of icy bodies beyond the giant planets. And when that happened, it did not happen quietly. Neptune's motion through that outer disk would have scattered huge numbers of icy objects inward and outward. The outer solar system became a source of bombardment. Comets, icy planetesimals, and rocky bodies were sent careening across the system. Some were ejected into interstellar space. Some were sent into the giant planets. Some entered the inner solar system, where the terrestrial worlds and the moon endured a prolonged era of impacts. This may be connected to what is often called the late heavy bombardment, a period around 3.9 to 4.1 billion years ago when the inner solar system appears to have experienced an elevated rate of impacts. The moon, with its airless surface and long memory, preserves much of that violence in its cratered face. Earth was bombarded too, perhaps even more intensely, but Earth's active geology erased much of the visible evidence. Still, the implication remains. The early habitable world was not gently nurtured into existence. It was hammered, and yet, once again, destruction and possibility were intertwined. Because the same bombardment that threatened young worlds may also have delivered some of the ingredients life would later need. Water, rich objects from the outer solar system, along with carbon-bearing compounds and organics, may have helped supply the raw materials that became Earth's oceans and prebiotic chemistry. The isotopic fingerprints of some of Earth's water suggest links to outer system sources. In that sense, the same chaos that could have sterilized surfaces may also have delivered the long-term foundation for biology. This is one of the recurring themes the solar system keeps whispering to anyone patient enough to listen. The mechanisms that appear purely destructive are often also the mechanisms that enable complexity. Jupiter may have nearly destroyed the inner system, then helped preserve its architecture. Bombardment may have threatened emerging worlds, then supplied ingredients those worlds needed. Instability is not always the enemy of habitability. Sometimes it is the price of it. Even now, the system is not perfectly secure. This is another uncomfortable truth. The present architecture of the solar system looks calm because we inhabit a short slice of time inside a configuration that is stable enough for civilizations to evolve. But stable enough is not the same as perfectly stable. When astronomers run long, term numerical integrations of planetary orbits, allowing gravity to play itself out over billions of years, with all the subtle mutual perturbations included, something strange appears. The system contains chaos. Not chaos in the sense of immediate collapse, not a dramatic unraveling waiting next week or next century, but chaos in the technical sense that tiny differences in initial conditions can lead to diverging outcomes over long enough timescales. The solar system's future is not absolutely rigid. It contains branching possibilities. Mercury is the clearest example. Its orbit is affected not only by the Sun, but by gravitational interactions with the other planets, especially Venus and Jupiter. Over billions of years, those interactions can produce resonances and instabilities in a small but non-zero fraction of simulations. In some scenarios, Mercury's orbit becomes so eccentric that the planet might collide with Venus, fall into the Sun, or be ejected from its current path entirely. The probabilities are low, but they are not zero. That matters, because it means the solar system is not a crystal locked forever into one eternal pattern. It is a delicately evolving gravitational system with futures that are similar enough to comfort us on human timescales, but not fixed enough to justify the word permanent. In extreme simulated cases, the instabilities can cascade. A changed Mercury orbit can perturb Venus. Venus can influence Earth. Earth and Mars can be drawn into altered orbital relationships. Again, these outcomes are unlikely in any single run of cosmic time. But their very possibility matters philosophically. It tells us that the present arrangement of the planets is not sacred. It is contingent. The solar system you know is one version of the solar system that could exist. That is perhaps the most disorienting lesson of all. We often imagine cosmic order as objective, inevitable, almost mathematical in a comforting way. But planetary systems are historical. Their architecture depends on formation paths, migration episodes, resonance captures, scattering events, collisions, and the timing of instability. Change the early migration of Jupiter, and Earth may vanish from history. Change the resonance behavior of Saturn, and the inner system may never recover. Change the late instability among the giant planets, and water delivery, bombardment, and the structure of the outer solar system may look radically different. This makes the current map of the solar system feel less like a law and more like a survived story, and survived stories always contain near misses. The Grand Tack is a near miss. Jupiter nearly erased the material that would become our world. The nice instability is a near miss, a late rearrangement that could have produced very different conditions in the inner system. Mercury's long-term orbital chaos is a near miss written into the future, unlikely but possible. The asteroid belt itself is a memorial to interrupted creation. Mars is a planet-sized reminder that growth can be arrested. Everywhere you look, the system carries traces of having almost become something else. There is a strange kind of fear in that, but also a strange kind of beauty, because the existence of Earth begins to feel less like a static fact and more like a narrow success. Not success in any purposeful or moral sense, but in the sense that certain processes happened to unfold in a sequence that allowed a habitable rocky planet to persist in the right place for long enough under the right conditions. No one arranged this. No hidden hand held Jupiter back at the last moment. No law guaranteed that Saturn would rescue the inner system. No promise ensured that bombardment would deliver more chemistry than catastrophe. All of it was dynamics, timelines intersecting, gravity making history. And history, even in the sky, is never neat. Perhaps that is why the solar system becomes more unsettling the more accurately we understand it. The old schoolbook version is calm because it removes the drama of formation and replaces it with finished positions. But the real system is still haunted by its own past. Jupiter's present calm does not erase its ancient migration. Saturn's rings do not reveal the role its planet may have played in reversing the course of the system's most dangerous giant. The asteroid belt looks like leftovers until you realize it may be a scar. The moon looks like a quiet companion until you understand the giant impact that created it. Everything in the solar system looks more stable from a distance than it really is. That, perhaps, is the central deception of all celestial beauty. Distance smooths violence into symmetry, and yet the violence matters because without it, we might not be here. Earth may owe its existence to instability that stopped just in time. It may owe its water to bombardment. It may owe its long-term survivability to a giant outer architecture that is chaotic enough to evolve, but stable enough not to destroy the inner worlds too quickly. The line between a life friendly system and a ruined one may be far thinner than we were ever taught. This becomes even more profound when you remember that planetary systems are now known to be common throughout the galaxy, and many of them look nothing like ours. We have found hot Jupiters skimming close to their stars, giant planets in eccentric orbits, compact systems of super-Earths, architectures that would seem alien if we compared them directly with the arrangement of our own worlds. That means the solar system is not the obvious default. It is one outcome among many. The grand TAC and related models help explain why our particular outcome looks the way it does, but they also hint at how easily it could have gone otherwise. A giant planet migrating too far inward could sterilize opportunity before it begins. A delayed instability could scatter worlds into ruin. Resonances could rearrange habitable zones, disrupt small, rocky planets, or deny them the long, quiet interval needed for life to become complex. The galaxy may be full of systems where the timing did not work out, which makes this system, our system, feel more miraculous in the non-supernatural sense, not because it was destined, because it was improbable and survived. Still, improbability is not the same as safety. The same deep dynamics that shaped the system in the past continue to operate beneath the apparent order of the present. Gravitational interactions never fully stop. Orbital resonances continue to matter. Small perturbations accumulate. The architecture of the solar system is not a monument. It is a current arrangement inside a living dynamical system, and that means the story is not over. Jupiter's ancient migration may be finished, but its influence is not. Saturn may no longer be rescuing the inner system from immediate destruction, but its gravity still participates in the long choreography of planetary resonance. The belt of asteroids still contains projectiles. The scattered disk and Kuiper belt still preserve populations of icy bodies that can, under the right nudges, enter the inner system. Long after the gas disk disappeared, the solar system remained capable of rearranging itself, and on the deepest timescales, it still does. What makes all this especially haunting is how utterly invisible it is to ordinary perception. You can look at Jupiter tonight and see serenity. You can watch Mars glow red and feel no hint that its small size may be the aftermath of giant migration. You can gaze at the asteroid belt only through imagination, because from Earth it presents no great visible scar in the sky, and never know that it may be the residue of interrupted planet formation. The sky offers composure. Physics reveals contingency. That tension is what makes the solar system so hard to stop thinking about once you begin taking it seriously. Every object has two identities, the one it shows now and the one it earned through violence. Earth is a habitable world, but also the survivor of a system that nearly prevented its birth. Jupiter is a majestic giant, but also the former executioner of inner planets that never existed because Saturn intervened soon enough. The moon is beautiful, but born of impact. The calm present is only the top layer of a much older story. And perhaps that is the true meaning of the grand TAC. Not only that Jupiter moved, but that the solar system itself was never a still machine waiting for life to appear. It was a dangerous evolving place where timing mattered, where the wrong resonance at the wrong moment could erase whole futures, where giant worlds could drift like threats through a young disk of possibility, and where what now looks inevitable was once balanced on an edge so narrow that we only recognize it billions of years later. So when you picture the early solar system now, do not imagine a neat row of forming planets passively circling a young sun. Imagine migration. Imagine near destruction. Imagine Jupiter turning inward like a blade, then outward again only because Saturn entered the story in time. Imagine a system that almost was not. A system that could have become one more dead architecture in a galaxy full of them, but instead settled, barely gently enough, into the version that allowed oceans, continents, and a species capable of reconstructing its ancient danger. And if that thought unsettles you, it should. Because the final truth is deeper still. All of this instability, all of this slow change, all of this near disaster may not be evidence that the solar system is broken. It may be evidence that dynamism itself is the reason life was ever possible here at all. What the solar system is actually telling us is not that everything is doomed. It is telling us that nothing has ever been still. That may sound like a small distinction at first, but it changes everything. Because across this journey, the pattern has repeated itself with almost unbearable consistency. The moon is leaving Earth. The sun is consuming itself. Moons in the outer system are being squeezed, heated, cracked open, and perhaps kept alive by the same tidal stress that will one day destroy them. Jupiter may have nearly erased the inner solar system before Saturn's intervention redirected the entire architecture of our world. Orbital chaos still lingers beneath the elegant order of the present arrangement, subtle enough to look harmless, deep enough to matter over billions of years. At first glance, all of this sounds like evidence of instability, decline, and eventual ruin. And it is. But it is also something else. It is the operating mode of a living system. That is the inversion at the heart of the whole story. We are tempted to imagine that a habitable solar system should be calm, fixed, balanced, preserved. We imagine safety as stillness. We imagine the ideal cosmic home as one in which nothing important changes. But the longer you look, the more impossible that picture becomes. The very processes that seem to threaten the solar system are the same processes that made Earth possible in the first place. Dynamism is not a flaw in the design. Dynamism is the design. Earth is habitable not because it escaped change, but because it was shaped by the right kinds of change at the right time. Take plate tectonics. To human beings, continents feel ancient and solid. Mountains seem like monuments. The crust beneath us appears stable enough to build civilizations on, and yet the Earth is moving from the inside outward all the time. Heat left over from formation, along with radioactive decay deep in the mantle and crust, continues to power a restless interior. That heat drives convection. Convection drives tectonic motion. Plates collide, separate, subduct, rise, and recycle the surface over immense spans of time. Oceans open and close. Mountain ranges rise and erode. Carbon is buried, released, trapped, and cycled back into the atmosphere. This is not a cosmetic feature of Earth. It may be one of the reasons our planet did not become Venus. Because tectonics participates in climate regulation. Carbon dioxide can be drawn down into rock through weathering and then returned through volcanism and subduction. The system is imperfect, but over geological time it acts as a stabilizing cycle, preventing climate from remaining locked forever in one catastrophic state. A truly static world might seem safer in the abstract, but in reality, a static world could become a dead one. If Earth had cooled too early, if its crust had sealed itself into rigidity without long-term recycling, if its interior heat had faded beyond usefulness, the planet might have lost one of its great climate-regulating systems. Stability in that case would not have meant paradise, it would have meant failure. The same is true of the magnetic field. Earth's magnetosphere is not some decorative halo. It is generated by movement inside the liquid outer core, where convecting iron creates a global magnetic shield. That shield helps protect the atmosphere from direct erosion by the solar wind. Mars, smaller and less able to sustain its internal dynamo over deep time, appears to have lost that protection long ago. Once the magnetosphere weakened, the atmosphere became more vulnerable, and the planet moved toward the thin, cold ruin we see today. Earth avoided that fate not by being inert, but by remaining active inside. The molten, moving core beneath our feet is not a threat to habitability. It is part of its protection. Again and again, the same lesson returns. The worlds that survive are not always the ones that stay quiet. They are the ones that keep functioning dynamically for long enough. Even the moon, whose retreat feels at first like a tragedy, has already played an indispensable role in making Earth the kind of world it is. The giant impact that likely formed the moon was an event of catastrophic violence. Nothing about it suggests grace. A Mars-sized body collides with the young Earth. Material is blasted into orbit. Debris gathers. A moon is born from planetary wreckage. It sounds like destruction because it was destruction. And yet from that destruction came one of the great stabilizers of our planet's history. The moon's gravitational influence helped steady Earth's axial tilt, moderating the kind of chaotic wobble that may have made Mars far more climatically unstable over long timescales. The tides it raised affected oceans, coastlines, perhaps even early chemistry, and the cycling of environments where life's first steps were taken. So what do we call that? Disaster, miracle, necessary violence. All of those words fail a little. The better word is process. Earth is habitable because process never stopped. The moon did not preserve us by remaining separate from history. It preserved us by being created out of history's most violent chapter and then participating in Earth's long stabilization afterward. Plate tectonics did not preserve us by freezing the planet into permanence. It preserved us by keeping the crust and climate coupled to a deep reservoir of motion. The magnetic field did not protect us by being static. It protected us by emerging from the constant churning of a metallic interior. Even Jupiter, that vast giant whose migration may once have nearly destroyed the inner system, may now help redirect or absorb some dangerous objects that would otherwise threaten the inner planets. The same world can be destroyer in one age and partial guardian in another. There is something almost unbearable in how completely this overturns ordinary human instinct. We want stillness to be safety. But cosmic history keeps insisting that survival belongs, at least sometimes, to things that remain active. That is why the solar system cannot be understood as a museum of objects. It is a web of evolving conditions. Every world is dynamic in its own way. Every orbit is part of a long negotiation. Every interior, every atmosphere, every gravitational resonance, every decay process, every source of heat and stress and motion contributes to the larger fact that this system is not simply sitting there, it is working. And perhaps the most extraordinary part is the timing. We exist during a very narrow window in that work. The sun is old enough to be stable on human and biological timescales, but not yet old enough to have driven Earth into irreversible sterilization. The moon is far enough away not to produce the savage tides of the earliest Earth, but close enough still to help stabilize the axial tilt that has kept long climate history relatively restrained. Jupiter sits far enough out to avoid destroying the inner planets now, but not so irrelevant that its presence fails to matter. Earth's core is still active enough to generate a magnetic field. The mantle is still dynamic enough to drive tectonics. The oceans still exist. The atmosphere still holds. The habitable zone still contains us. None of these things were guaranteed. That is one of the hardest truths to let settle. We are living at the intersection of multiple independent timelines, each one evolving according to its own physics, each one temporary. The sun's brightening, the moon's recession, Earth's tectonic vitality, the persistence of the magnetic field, the architecture of giant planets, the delivery and retention of water, the stability of long-term climate feedbacks, all of these processes overlap for a while. And in that overlap, complex life becomes possible. Not forever, not by cosmic right, just for now. This should not make existence feel smaller. It should make it feel almost impossibly precise. Because the more closely we look, the less the Earth resembles a default outcome, and the more it resembles a temporary agreement among moving parts. A star in midlife, a moon still close enough, a planet still geologically alive, a climate system still capable of regulation, a solar system architecture stable enough for deep time, but not so static that essential processes were shut off before biology had its chance. We do not live in a timeless paradise. We live in a fleeting corridor of compatibility, and that corridor may not be unique. This is where Europa and Enceladus return to the story, not as side characters, but as the deeper expansion of what habitability might actually mean. If life exists in the dark oceans beneath the ice of those moons, then the meaning of life in the universe changes fundamentally. Because then life is not just something that emerges on a temperate, rocky planet under sunlight, within a narrow, classical, habitable zone. Life would instead appear as a chemical process that can emerge wherever conditions allow it, whether beneath skies like ours or beneath kilometers of ice in darkness far beyond the warmth of a star. That possibility is almost too large to absorb at once. It would mean that life is not necessarily rare because Earth is special in the old poetic sense. It may mean Earth is one expression of a broader physical tendency. Give chemistry enough complexity. Give it liquid environments. Give it energy gradients, time, and protection from complete annihilation. Under some subset of those conditions, life may happen. Not magically, not miraculously in the old sense, but lawfully, as an extension of chemistry into self, organization. And if that is true, then the universe is not merely capable of life. It may be inclined toward it. Europa, Enceladus, Titan, perhaps even other hidden worlds we have not yet fully understood, begin to look less like anomalies and more like reminders that our first map of habitability was provincial. We assumed life would require what life on Earth visibly uses most: surface water, moderate sunlight, breathable skies, the familiar arrangement. But the solar system keeps widening the definition. It keeps showing us that tidal stress can stand in for sunlight, that oceans can survive under ice, that chemistry can flourish in alien cold, that the inventory of possible living environments may be vastly larger than our instincts were trained to accept. This is why the solar system's constant transformation is not just a threat. It is the source of possibility itself. Without tidal forces, Europa may be a frozen tomb. With them, it may hide an ocean. Without internal heat, Earth might have become geologically dead. With it, tectonics and magnetic shielding remain active. Without ancient migration, bombardment, and giant impacts, Earth might never have formed as it did, might never have gained its moon, might never have inherited some of the materials that made oceans and carbon chemistry possible. The same system that is gradually dismantling itself is also the system that made living complexity possible. That is the paradox the night sky does not reveal unless you study it long enough. Destruction and habitability are not opposites. Often they are neighbors. Sometimes they are the same process viewed from different moments in time. A moon spiraling inward may one day become a ring, but before that, tidal stress can warm hidden seas. A star brightens toward the death of one biosphere while briefly making farther regions more temperate. A giant planet can threaten the inner system in youth and help shield it in maturity. Instability can end worlds, but it can also create them. The solar system is not sending us one simple message. It is telling us that complexity survives in motion, not in stillness. And perhaps the most moving part of all is that we are here to notice it. That fact should feel stranger than it usually does. A species with lifespans measured in decades, living on a planet that is 4.5 billion years old, inside a solar system about 4.6 billion years old, under a star that will continue for billions more, has learned to reconstruct processes that operate on timescales almost absurdly beyond intuition. We have measured the moon drifting away. We have traced the sun's stellar evolution. We have inferred ancient migrations of giant planets from the surviving architecture of the worlds around us. We have sampled plumes from hidden oceans on distant moons. We have understood enough to realize that what looks stable is often only slowly transforming. That is not a trivial achievement. It may be one of the most extraordinary things happening in the solar system right now, that matter arranged itself on one small world in such a way that it became capable of understanding the larger system that formed it. In a universe where stars burn, moons recede, atmospheres erode, and orbital dynamics reshape the fates of worlds, consciousness emerged long enough to see the pattern. That does not stop the transformation. It does not save the sun from aging, or the moon from leaving, or Earth from one day becoming uninhabitable, but it changes the meaning of those facts. They are no longer merely events. They are known events, witnessed events, understood events. There is a quiet dignity in that. The solar system is changing and we cannot stop it. But we can know it. We can see that our world is not blessed because it is static, but because it is dynamic in a particular way at a particular time. We can see that the same forces that will one day erase habitability are the forces that once enabled it. We can see that life may not be a miraculous exception pinned to a narrow strip of distance from a star, but a deeper tendency, waiting wherever matter and energy are allowed to converse long enough. We can see that our existence belongs to an intersection, narrow, temporary, and astonishing. So when you look up at the night sky now, do not imagine a still machine. Imagine a system in motion. Imagine the moon retreating, the sun brightening, the hidden oceans turning under ice, the giant planets carrying the memory of ancient migrations, the gravitational negotiations never truly finished. Imagine apparent order, resting on top of ongoing transformation. And then imagine that this transformation is not evidence that the solar system is broken. It is evidence that the solar system is alive in the only way a system of worlds can be alive, through process, through change, through the endless rearrangement of matter under law. That is what the solar system is actually telling us. Not that everything ends, but that everything meaningful begins, survives for a while, and becomes something else. And that may be the most beautiful and unsettling truth of all. If this reached you tonight, subscribe to Nocturnal Space, turn on notifications, and leave the word dynamic in the comments.